Hello, I'm Anthony Leboissetier. I'm working at NASA GIS in New York City on the ocean and sea ice components of GIS Modeli, our global climate model. And I started more recently collaborating with our Rocky 3D group on developing a version of our global climate model for icy moons with subsurface oceans. Think Europa or Enceladus in our solar system. So here is a collection of current, past, and potential ocean worlds just in our solar system, from the surface oceans of current Earth to ancient Mars or Venus for planets with an atmosphere, to the subsurface oceans of the icy moons Europa and Enceladus, to the different layers of oceans sandwiched in between layers of ice on Ganymede, to Pluto, and even more recently, Ceres, which was just added to this list a few weeks ago as potentially harboring a subsurface ocean. Moving outside of our solar system, there is an ever-growing list of exoplanets added each year to the catalog. And out of all these planets, recent studies have shown that quite a high fraction of these worlds could be host to a liquid ocean, including planets like Proxima b, Kepler 11c, and multiple planets of the TRAPPIST-1 system. Which is why the amazing variety of exoplanets potentially harboring a surface ocean or a subsurface ocean requires that we revisit some of the assumptions that we've been using for years or even decades while developing a global climate model for Earth's ocean. Some of these assumptions and considerations that we'll visit here today include the use of a slab versus dynamic ocean, the implication of modeling a deep ocean, having to update the equation of state, and the inclusion of geothermal heating. Now, slab ocean models have been used coupled to atmospheric GCMs to successfully understand the sensitivity of a climate system when using the mixed layer as the dominant process. But a dynamic ocean, while more computationally expensive, is required to fully understand the global ocean circulation and its interaction with the atmosphere. Where a slab ocean in this simulation on the left by Hu et al. Of a tidally locked planet can only predict an eyeball configuration where only the ocean on the side facing the sun is melted. It totally misses the heat transport to the other side that can be captured now on the right by a fully dynamic ocean that allows some of the sea ice to be melted on the far side. Another assumption that we should reassess when moving to an exoplanet oceans, whether at the surface or subsurface, is the use of the hydrostatic form of the equation of motion that were developed for global climate models on a planet with a shallow ocean like Earth. And they were developed starting from the non-hydrostatic equation of motion in spherical coordinates that we have here in the top rectangle for the horizontal component of the velocity on the left and the vertical velocity W on the right, with expressions for Gu, Gv, and Gw below that contains the advection, metric, Coriolis, and forcing terms. Now, considering that the ratio between the ocean depth h and the radius of Earth is quite small on one side, and that the vertical component of the velocity w is relatively small when compared to the horizontal velocities on the other side, assumptions like considering the variable r constant and equal to the radius of the Earth in this equation, and simplifying the expression of the Coriolis force were meant to transform this equation of motion in a more GCM, computationally friendly form that we call the hydrostatic primitive equations, or HPs, that basically consider Earth oceans in a state of hydrostatic balance where the pressure field is balanced by the gravity force in the ocean. Moving to a planet or a moon with a deep ocean, meaning tens to hundreds of kilometers, as it might be on one or more of the TRAPPIST-1 planets, forces us to review some of these assumptions. For example, if we consider the oceans of Europa and Enceladus in our solar system, we can see that the ratio between the ocean depth and the radius is much higher than for Earth, with the ocean of Enceladus being probably almost more than a tenth of the radius when compared with a ratio of only 6 × 10⁻⁴ for Earth. So we need to reestablish some of the neglected Coriolis and metric terms, as well as relaxing the shallow water approximation by re-enabling r as a variable and not just a constant. And we land on an intermediary form of the equations of motion that we call the quasi-hydrostatic equations. That is physically more realistic for 100-kilometer deep ocean than the purely hydrostatic form, but not as computationally expensive as the full non-hydrodynamic ocean model. And we can understand the importance of some of these neglected terms for the Coriolis force if we consider, for example, a parcel of water rising by 100 meters. This term would represent an additional retrograde velocity delta U of about 1.2 centimeter per second per 100 meters at the equator, which might be somewhat negligible in a shallow ocean, but has to be taken into account for deep oceans. Though it should also be noted that some people are pushing the community to adopt the quasi-hydrostatic set of equations for Earth as well. So I plotted here a simulation that I'm currently running using the quasi-hydrostatic form of the ocean that I implemented in Rocky 3D. I'm running this on Earth for development purpose before switching to a deep ocean configuration in a 2 by 2.5 degrees ocean with 32 layers. So with Earth, we're not expecting a lot of differences when compared to the regular hydrostatic control run. We have here the difference between the quasi-hydrostatic run and the hydrostatic control run for the surface temperature on the left and surface salinity on the right, as well as the zonally average vertical structure for temperature and salinity for the Atlantic Ocean on the bottom row. And it seems that the somewhat minimal impact on the temperature and salinity fields of including the missing Coriolis and metric terms, as well as relaxing the shallow water approximation, at least in our Earth configuration, seems to be mostly localized in the Gulf Stream and ACC regions. It would be quite interesting to perform the same comparisons between the hydrostatic and quasi-hydrostatic oceans once we switch to a deep ocean. And we're planning to use Europa as a first test case with Rocky 3D. Continuing our review of processes that need to be reevaluated for exoplanets ocean is the equation of state that relates the density, pressure, temperature, and salinity. Importing directly the equation of state developed for Earth ocean GCMs into another planet ocean is an easy first step, but this could oversimplify the role of salinity in the general ocean circulation, as different values of salinity could lead to totally different ocean circulation, with the water being transported from the poles and sinking at the equator, for example. Going back to the deep ocean, the extremely high pressure at the seafloor depth, which could go down to 800 kilometers on Ganymede, would create a layer of a form of ice that would prevent the ocean from interacting with the rock beneath and lower the overall salinity during the planet evolution. On the other side, ocean with a higher salinity might lead to a reduced sea ice coverage and directly to a reduced albedo as the melting temperature of ice decreases. Finally, geothermal heating at the base of the ocean needs to be reassessed, as it sometimes is an essential driver of the very existence of the ocean. In the case of subsurface ocean, it's the geothermal heating, whether from tidal heating or radioactive decay origins, that first creates and then sustains a liquid ocean from freezing entirely. And speaking of the new version of Rocky 3D, we can now specify a map as a netcdf file of the geothermal source on the seafloor. Work has also been done in the past to parameterize the heat plume rising in the deep ocean, as in Goodman et al. In 2004, and this would also need to be included when modeling exoplanets ocean. So transitioning from Earth-centric GCM simulations to exoplanets ones brings a host of assumptions that need to be revisited as far as the ocean is concerned. Some additional refinement will come over the next few years from increasing the vertical and horizontal resolutions on exoplanets to allow for more realistic vertical mixing schemes and mesoscales resolving simulations. We should also welcome the fact that Earth and exoplanet modeling are not a one-way street and can immensely benefit from one another, as using ocean models developed for Earth on other planets serves as a great stress test / debugging tool as it pushes our models to their limits. Thank you.